Birmingham. He's going to be talking about structured learning with temporal Gaussian mixture for model-based reinforcement learning systems. So yeah, feel free to start.
Thanks. Thanks for the kind introduction and the opportunity to speak today. So as you mentioned, I will be speaking about structured learning with temporal Gaussian mixture for model-based reinforcement learning systems. So this work was done in collaboration with Mike Jesch and Howard Bowman, which are my supervisors. So the first thing I need to explain is what is reinforcement learning. And put simply, you have two entities. You have an agent, which takes actions in the environment, and you have the environment, which provides observations and rewards. So the observations are used for actions, which produce the next observation and the next reward. The goal of the agent is to maximize the return, which is here at the bottom of the slide. And the idea is that the return is the sum of future discounted reward. So gamma here is the discount factors, which reduces the importance of future rewards far into the future. And R2 is just the reward at time step 2. Now, not only do we want to maximize reward, but we want to also create a model of the environment. In this presentation, the environment is going to be a 2D maze like this one. The mouse is the starting position of the agent. The cheese is the goal state. And you can move around like in a normal maze. So go left, right, up, bottom, or just hit when you are in the final state. The goal is to learn how many cells there are in the maze and also how they are connected to one another. So you want to learn the number of cells and the connectivities between the cells. Maybe getting something like on the right-hand side, where here you have a mixture of Gaussians, and each Gaussian is centered around the different positions. Because what the agent is observing is a noisy estimate of its current position. So if it's in this cell, it's going to get an observation which is centered here, but with some kind of Gaussian noise around that. So more precisely, the model we are going to learn is a partially observable Markov decision process, where the continuous observations of the agents are at the bottom. And then we are going to try to extract some latent variables. The variables z here is discrete and has as many values as the number of components. One thing to mention is that we are trying to learn how many components there are, so the number of discrete values z can take is going to evolve as we are learning the model. D here corresponds to the standard D vectors in active inference, which provide a prior over the initial state, and B is a standard matrix in active inference, which basically there is one matrix for each possible action, and they define the temporal transition between time steps. Mu is going to be the mean of the Gaussian component over there. So the first mu will be here, second, third, and so on. And lambda is going to be the precision matrix of the different components. So it's going to define the shapes of the individual Gaussian components, whether it's circular or more elliptic. Okay, so that's the overall model, but for stability, like to make it more stable, we decided to train the model in 2 bits. The first bit is the perception model, and the second part is the transition model. So perception first and then transition. First, I'm going to explain what the perception model.
Sorry, should we say that even though this is reinforcement learning, we are interested in active inference, maybe doing an active inference as well, yeah? Just to put that on the table.
Yeah, so for now, we kept it simple because it was already quite hard to learn the model, but obviously we can replace the reward objective with the expected free energy and get an active inference agents on these stats. That's a good point indeed. Thanks, Howard. So in terms of the perceptual model, so as I already hinted at it, it's a mixture of Gaussian, and we are using the mean shift algorithm to cluster the data points that we are collecting. So the way it works is that for each data point in the dataset, you start with a point centered on that data point. You draw a circle around it, compute the mean of all of the points that lie within the circle. This gives you a new position from which you can draw another circle, compute the mean of the point falling inside this new circle, and so on and so forth. And you do that until this process converges to a point, and then the point which converges to the same point in space are going to be clustered together. So if you do this process on this point, you will end up somewhere here, this point somewhere here, this point somewhere here. So all of those points are going to be clustered into the green cluster over there. And we are going to use that to initialize our Gaussian components. Okay, so to be a bit more precise about this perception model, this is its structure. We already discussed the different variables. D is like an active inference distributed according to a Dirichlet distribution. The state is a categorical distribution parameterized by D. X is going to be distributed according to a mixture of Gaussian. This mu is going to be distributed according to a Gaussian distribution, and lambda is going to be a Wishart distribution. The idea is that all of those distributions are set in a way that we have conjugacy in the model, and I will come back to that. But first, I want to delve a bit deeper into the different factors and how they are defined. So I mentioned that X is distributed according to a mixture of Gaussian. So this is the equation. The first product is just going to iterate over all data points in the dataset. So for the sake of explaining, we are just going to focus on one data point, so we can ignore this product. The second product is going to iterate over the different components. Okay, so maybe component 1, 2, and 3. Z and K is going to be equal to 1 if the data point of interest is associated to the kth component. Here it is associated to the first component, so we have 1 here and 0 otherwise. And so what this product is doing is just selecting one of the Gaussian distribution and computing the probability of the data point according to this one Gaussian. So that's what we mean by the data is distributed according to a mixture of Gaussian distributions. And the other important factors here is the discrete distribution Z, and this is really just a categorical distribution. So each component that we had in this slide, it has its own prior probability. Okay, I also mentioned this notion of conjugacy, which will be central to this presentation. The idea of conjugacy is a bit like a couple having a child, and the child looking very similar to one of the parents. For example, here we have a prior, which is a Dirichlet, and we have Z given D, which is in this context the likelihood. And when they combine to form a posterior distribution, they form a child, which is another Dirichlet. And what's important is that those parameters are like those two, as both are like Dirichlet distributions. So those parameters could be copy and pasted to the prior, and this will become useful in the remaining of the presentation. Okay, so why is conjugacy useful? It's useful to perform inference. You could perform inference in order to compute the posterior using just Bayes' theorem, which gives you the posterior is equal to the likelihood times the prior divided by the evidence. But this evidence requires a marginalization, which when we have continuous variable turns into integrals, and this can be untractable. So instead of using this Bayes' theorem, what we do is that we introduce a variational distribution, which approximates the true posterior. And the goal is to make the approximate posterior as close as possible to the true posterior. Okay, so graphically, we have a potentially complex distribution in red, and we try to approximate it with a simpler one, which is Q of S. The problem with this approach is that as we collect more and more data points, the inference time is also going to go up. And so because we are trying to do real-time decision making, this becomes a problem. So what we are going to try to do is to remain with a small number of data points, so stay on the left of this graph. But as we forget some of the data points to stay on the left, we need to do it in such a way that we don't lose the information provided by these points. So how can we do that? And also, a second question is going to be, what data point do we even want to forget? Okay, how do we do this decision of what do we keep and what do we forget? For now, I'm going to assume that someone arrives and splits the dataset for us, and later in this presentation, I will explain how the split is actually performed. But let's assume that the entire dataset is split into two sets. The first are the data points that we are going to forget. The second one are the data points we are going to keep. In order to integrate the information of the data point we want to forget and to not lose the information, we first introduce a notion of empirical prior. This empirical prior is really just a posterior distribution which contains all of the information provided by the point to forget. It's called a prior because it's going to be used as a prior, but it's empirical because it's based on the data. Now its factorization is like this. It's like the definition of the factors mirror the one in the prior. So Z was a categorical, it still is. D was a Dirichlet, it still is. Mu was distributed according to a Gaussian, it still is. And this is still a Wishart distribution. Now, in addition to this empirical prior, we also have a full posterior, which, so this is a variational posterior, which takes into account the entirety of the data points, and it has the exact same factorization. So I'm not going to discuss that further. Now, how do we compute all of those distributions? We just use variational inference as usual, but we do that in two steps. First, we start with the prior and the likelihood, and we compute the empirical prior through variational inference. Then when we have this empirical prior, we use it as a prior, and we keep the same likelihood, and now we are integrating the other half of the data point, the one we want to keep. When we have performed this second round of inference, we are now here with a variational posterior, which can be used for decision making. But once again, we are going to come back to that. So so what can we expect out of this model? Here I've initialized the components using the k-mean algorithm. So there are too many components for the true number of clusters in the data. And as we perform inference, we can see that the algorithm is able to discover that, in fact, there are only 3 clusters. 3 components are supported by the data. The other aren't. And so it's able to simplify the model. So that's the kind of thing you can expect from this mixture of Gaussian. Okay, so that was the perceptual model. Now, not only do we want to learn, how many components there are and where they are located, we also want to understand the dynamics and how we can move from one component to another. This is a transition model. If you remember one of the first slide, this is how it looks like. We have the prior over the initial state, which is Dirichlet, and then we have, most importantly, the B matrices, which explain which models how you move from the states at time 0 to state at time 1, given the action that you are performing in the environment. This is the exact same B matrix as in active inference, so I'm assuming that some of you will be familiar with that. Now, how do we create data points for this model? First, we have the continuous observation that the agent is making. Then we feed them into the perception model to get posterior distributions over the latent variables. So we turn a sequence of continuous observations into distributions over the state at time step 0, 1, 2, and so on. But in order to train this transition model, what we need is like tuples of consecutive states. So we turn this sequence of states into tuples of consecutive states. So we first group together Z0 and Z1. This will become our first data point. Then Z1 with Z2. This will become our second data point, and so on. Okay, so now we are in the business of learning the dynamics. And once again, we want to do it in a way which is optimized. Here, I just want to illustrate the transition mapping very quickly. The idea is that everything is stored in a matrix. So this is one matrix for one specific action A. And for example, a high probability in this matrix will mean that we are very likely to move, to remain in the same component here. We at time step 0, we are in component 0, and we stay in that component with a high probability of 90%. Okay, but as I was saying, when we are learning this model, we want to do it in such a way which allow us to forget some of the data without losing the information which they provide. So once again, we assume that all of the dataset has been split somehow, and then we will explain how the split occurs. And once again, we have this empirical prior, which is going to be integrating the information from the data point we want to forget. And then we have the full posterior, which is going to integrate the data, like all of the data points. In terms of the structure, we once again mirror the distribution from the generative model, which means that B is still distributed according to a Dirichlet, D is also distributed according to a Dirichlet, and those are both categorical distributions. And here I just wanted to show this equation, which I think is very similar to what we have in active inference, just to explain that having two posterior distribution, more precisely the empirical prior and the posterior, does not increase the computation that needs to be performed. And the reason is because of what is on this slide. So the way you compute the empirical prior parameters, which are over there, is just by taking the prior parameters. So this is the number of times we have already seen a transition from component K to component J when taking action A. And to that number, you are going to add the probabilistic count of how many times you moved from component K to component J when performing action A. But this count is only going to be performed over the data point that we are going to forget. In active inference, you will do it over the entire data set, but here it's only the data point you want to forget. Yeah, and when you add the prior count to the number of transitions in the data point to forget, you get the empirical prior parameters. Then the empirical prior parameters are going to become the prior parameters in the equation. And now you keep counting, but this time in the data point that you want to keep. So exact same equation, but with a different set of data points. And this integrates the information from the other, the second part of the data set and leads to the posterior parameters. So those are the posteriors, the parameter of the posteriors, which we can use then for decision making. In terms of what the model can do, so we already saw what the perception model can do. This is the kind of thing that you are going to learn out of the perception model. You can learn how many components there are and also where they are located. Now, the transition model is really about learning how you move from one component to another, depending on the action taken. So if we focus for a minute on this matrix, which corresponds to the action going down, we can see that the agent has learned that with high probability, if you are in state 0, 1, 2, or 3, you will remain in those states if you are trying to go down. So from 0, you move to 0, from 1, you stay to 1, 2 to 2, and 3 to 3. And this is because all of those components are at the bottom. There is a wall below it. So if you try to go down, you remain in the same position. However, if you are in state 4, you can see that the model predicts that you will end up in state 3 with high probability. And this corresponds to the fact that there is no wall below 4. In fact, there is a state 3. So this is basically confirming that the model understands dynamics of the environment. So for now, we have assumed that someone arrived and split the dataset for us between, into two sets, the one we want to forget and the one that we should keep. In this section of the presentation, I want to explain how this process is actually performed. So when it comes to this forgetting, there is a notion of plasticity versus stability. This notion of stability versus plasticity comes from the notion of, put simply, each component in the Gaussian mixture can be of two kinds. Either it's flexible, in other words, it's plastic, or it's fixed, in other words, it's just stable. Okay, so all the red components here are stable. So each new component, each component in red are flexible. So they are initialized flexible. And then as they keep persisting over time, so the more we see them, the more likely they are to become fixed components. So how do we do that? So if we are the agents, we are going to start by collecting 100 data points. These are hyperparameters, and this is 100 data points. We will then perform the mean shift algorithm, and we are going to extract 4 components out of those 100 data points. Then we go back to the environment, collect some more data points. This time we have 200 of them, which are represented on the right. And we can perform mean shift again. This time we find a few more components. Now the question is, how do we know whether a component has persisted over time or not? What we are doing is that we are matching the component on the left-hand side with the component on the right. So this is a Gaussian distribution. This is a Gaussian distribution. We can compute the KL divergence between the two. And if this is inferior to a threshold, then we are going to consider that this component has persisted over time. And in order to know how long a component has been around, we just have a counter and we increase the counter. Okay, so this one was there, we now have seen it twice. This one was there, we have seen it twice. But this one is a bit too different from those two components here. So it is not recognized as the same components, and those are considered as new components. And then we keep collecting some data, keep doing the tracking, and eventually some components are going to become quite old with respect to this counter. If you have seen a component for more than 5 times, that's another hyperparameter, then it becomes stable. So it used to be flexible, now it is stable. Okay, so now that we have this notion of flexible and fixed components, how can we use that to know what we can forget or what we should be keeping? So this is a representation of a typical run in the environment. You have the start of the trail on the left and the end of the trail on the right. Now you have the observation at the bottom. Okay, so each time you take an action, you get a new observation, you take a new action, a new observation, and so on and so forth. And over there, you see the responsibilities. So this is basically the distribution over the latent variable. So you have the observation. Here you have the latent variable, which tells you in which component is responsible for this observation, which component, to which component the observation is associated to. If this component is fixed, we have a black circle. If it is flexible, it is a red circle. Now, in order to understand what we can forget and what we should keep, we need to imagine what would happen if we were to lose this data point. If you lose this data point, then you won't be able to use the perception model to reconstruct, to compute the responsibilities anymore. So you will lose the ability to compute R0. Now, if you lose the ability to compute R0, then you won't be able to learn the transition between R0 and R1. So the condition that you need to have in order for a data point to be forgettable is that you need its neighbors. What by that I mean the previous observation and the next observation, as well as the current observation, to all be part of fixed components. So for example, if you're at the beginning of the trio, you need x0 and x1 to be associated to fixed components in order for you to be able to forget x0. So now I can explain that the blue circle corresponds to things you can forget, and the white circle corresponds to things that you must keep. Okay, so that's how you split the dataset into two parts. Now, on the bottom of the slide, you see whatever is left once you have removed the thing you can forget. So this is the remaining dataset, the dataset you want to keep. Okay, so for now, I've explained how we can learn, the number of components as well as their positions and all these kind of things with the perceptual model. How we can learn the transition between the components depending on which action you are performing. This is done using the transition model. And then I have explained how you can optimize the inference by integrating some of the data points into the prior. But this is not enough to have behaviors. We now need to know how do we perform actions. Okay, and we do that using reinforcement learning for now. This could be done using active inference. So more precisely, we use Q-learning. The idea of Q-learning is that we are going to try to learn what is called a Q-value. So Q-values is just, okay, so the Q-value is, you can think about it as a table, right? Where there is as many rows as action and as many columns as states. And each cell in this table is going to be the expected reward that you are expecting to get if you take this particular action in this specific state. So it's basically an estimation of the return that the action or that the agent is expecting to get. So how do we compute this? The first equation here is the standard equation in reinforcement learning for Q-learning. In order to compute the new Q-value, you take the old Q-value and you add to this lambda, which is the learning rate, times a temporal difference. So this is the learning signal that is added to the old value to get the new value. Unfortunately, Q-learning is initially defined for Markov decision processes, where the states are known. In our case, we only have a distribution of states. Right? We get this distribution of state using the perceptual model. So we update this equation and we weight the learning signal by the probability of being in that state. Now, I mentioned this temporal difference, but I need to explain what it is and how it's actually providing some kind of learning signal. So as the name suggests, it is a difference between two terms. The first one is over there, and it corresponds to the targets, what we are trying to predict. The second term is over there, and it is our current prediction of the return. Okay, so what is the target? The target is just the reward that we are going to get if we take the action, an action in a specific state, plus this is the discount factors which discount future rewards, times the actual expected future rewards. Once again, because we don't know what state we will be in the future, we need to use the transition model in order to compute the expectation of future reward. And then future reward is estimated with using our current Q values, but this time on the future state, and by assuming that we want to maximize future reward, so we take the best action, 80. So just to summarize, the temporal difference is just a difference between a target, which is an estimation of future return, and our prediction of this future return. You can organize those inside a table, which has as many rows as action and as many columns as states. Now, in order to compute this equation, you first need to weight the temporal difference by the posterior probabilities. So you have your posterior of a state, you weight that with the temporal difference corresponding to the action you have taken in the environment. And then you weight that by the learning rates. Now you have this term that you need to add to the previous Q values, the old Q values over there, to get the new Q values. So that's how Q learning is being performed. So what kind of result can you expect from this approach? So here we have 6 different mazes, and TGM is Temporal Gaussian Mixture. It is our approach in blue, and DQN is like standard reinforcement learning benchmark. A to C is another reinforcement learning benchmark. The first thing to mention is that we are only giving the agent 5,000 data points, so a very small amount of data points. And this is why some of the reinforcement learning benchmark are sometimes unable to learn the task. Our goal is to learn those environments in a data efficient manner, and also to learn a model, which is not given by those benchmarks. Those are called model-free reinforcement learning techniques. They just tell you what action to take, not how it does not model the environment. Okay, so if we look at this first maze, we see that our approach is learning faster than Q learning, but that DQN, but DQN is solving the task almost as well as our approach. In this second maze, we are once again a bit faster. DQN is doing exactly the same in terms of performance, just slightly slower. Now, as the maze becomes bigger, then our approach starts to struggle, and we will come back to why that is shortly. DQN still manages to solve the maze. And the final example is this maze. Once again, we are able to solve the maze, just slightly slower than DQN. The last 2 mazes that I've not been discussing so far represent 2 different limitations of the approach. The first one here, and to explain what the problem is here, I need to explain the colors. Okay, so here we had only green cells. Those cells correspond to the model being learned properly. So for those cells, the model has been able to learn a Gaussian component centered on that cells. It has been able to learn the dynamics as well. A red cell, like over there, means that the model has never been able to learn a Gaussian component. Maybe it just never moved there in the first place. But an orange cell means that the model was once learned, but then because there was too many states, those components either join with their neighbors or collapse. In other words, they got unlearned. So now that you understand the colors, the problem is pretty clear. What's going on is that as the number of states becomes too large, the model becomes unstable, and as the agent does not understand the dynamics of the environment, it becomes unable to solve the task. Now, one way to solve that would be to have some kind of hierarchical model which splits space into smaller chunks and then learn one of those models for each chunk. The second model, the second problem is harder. It is so hard, in fact, that none of the approach, not even the reinforcement learning benchmarks, are able to solve it. What makes this approach so hard is that in order to get to the reward in the first place, you need to take a lot of action in the right order. There's a very, reward is very sparse in this environment. So that's why reinforcement learning benchmarks are unable to solve this environment with a small number of data points. Our approach does not solve the task because it is not able to explore far enough into the maze. So once again, in order to explore further, you first need to get there. So you need to have a lot of action, right? And then you can start exploring from there. This is really about exploration strategy. And this raises the question of how should we explore in the environment. Okay, so that's so that's the second issue. Okay, so I want to summarize a bit the entirety of the approach, and this is my last slide. So as you saw, our model is split into two parts. The first part is the perception model, which learns the position of the Gaussians as well as their shapes and how many Gaussian there are. This is our mixture of Gaussian distributions. Then we have the transition model. The transition model is going to learn the dynamics. So how do you move from one Gaussian to another depending on the action that you are taking. Now, in order to perform inference in an efficient manner, in order to do that, you need to keep track of the components. And you need to know whether a component is here to stay or whether it's still very early to say. So this is why we have flexible and fixed components. And we have this tracking system that updates the type of component we have. And then based on that, we're able to split the data set into two parts, the data point we want to keep and the one we want to forget. The data point we want to forget are used to compute the empirical prior, which are going to improve the models, both the perception model and the transition model. And then the entirety of the data set is used to compute the empirical, the approximate posterior. And this empirical variational posterior, is going to be used for behavior in order to compute the Q values. And obviously, then you do reinforcement learning and maximize take the action which maximizes the Q values. So yeah, that's about it for me. If there are any questions, please do not hesitate to ask.
Thank you so much, Theophile, for your presentation. It was very nice. So now we are gonna start the Q&A session. So if there are any questions or comments, feel free to jump in. So I have like a general question at the end that you said, if as you increase the number of states, it becomes like unstable. So you should do some kind of hierarchical planning, as you said, like dividing the states in, like subsuming some states on more like coarse graining states, so that you could do some sort of planning across them or something along those lines.
Yeah. So yes, the idea, for example, is that this this model, so the mixture of Gaussian, has a tendency to absorb neighboring states together. So if you have a corridors, for example, here, you could have a Gaussian which will start taking control of this corridor. So this could be a way to basically create a hierarchy. You first learn the corridors, and then you learn a model of each corridors individually. So that would be one way to expand the problem, to solve this problem. Now, for very open kind of areas like this, you will have to find another way to do this hierarchical modeling, maybe just based on distance. So components, as you start learning the components which are close together get clustered together in another level of the hierarchy. So that would be another way.
Okay, cool. Thanks. Howard?
If others have questions, they should go first, because I see Theophile a lot, but if there's none, I'll ask mine.
Yeah, I guess just go ahead and we will.
Yeah. Okay. So Theophile, yeah, I was just pondering on the bottom, the maze at the bottom right. Yeah, this big open.
Yeah.
So it's literally unlearning, right? It's sort of learning and then unlearning.
Yeah, exactly.
So
yeah.
So if you're able to fix the Gaussians, could you stop that unlearning? Do you see what I mean? If you change the threshold, if you change the threshold at which you forget, could it work? Do you see what I mean?
That's a good question. It could be. I guess it depends exactly what's going on. I think when I was debugging this issue, what tends to happen is that sometimes some component will specialize for some of the data points. So for example, imagine you have this kind of data, and then you get 2 new points in these components. If you just absorbed all of the data points into the prior, because it was a fixed component, then those 2 data points you just get are the only one you are going to get for this particular point in space. And so the mean shift algorithm is going to create a component for those 2 data points. So it's specialized to those exact 2 data points. It has a better fit than the other broader components. And the problem is that this new component is not going to be matched as being like a continuation of the old components. So here we are matching components between time step. And if they are the same, we just increase a counter. What's happening is that on top of this components, there is another component which is specialized for those new data points. And if they persist, they can disturb the model. Like they start taking responsibilities for data points that should be attributed to the already existing components.
So it is to do with the fixing. It is to do with
I
that.
think it is to do with the fixing.
So one could maybe think of a better, sort of unfixing and things like that.
Yeah, or like maybe even like, if you have new components, you could compute the Keil divergence, and you could say if the Keil divergence is, close enough, like small enough, then you just discard this new tricky component, let's say. So having another threshold, you have 2 thresholds. The first one would be, how do you know whether the component on the left is the same as the component on the right? And the second threshold would be, okay, but even if they are not the same, are they similar enough that they are actually occupying the same part of the space? And so in this case, the newest one should just be discarded. Yeah.
Okay.
Another approach would also be just don't integrate all of the data points. Just keep a few data points associated to this component just for stability. So some kind of prototypical like typical data points that you keep just to maintain the component here quite broad.
Great. Yeah.
Tim, go ahead.
I was wondering how your observation and action space works in these mazes. So I assume that your observation space is like a continuous XY coordinate, but then your action space is still like some discrete kind of grid world movement, or is this continuous as well?
Okay, so that's a good question. Thanks for asking. So as you mentioned, the observation are continuous. It's just the 2D position of the agent. we are extracting discrete latent spaces. So those are discrete latent variables at each time step, and the actions are also discrete. This is because of how our environment works. For now, it's just there's a discrete set of actions, up, down, left, and right. Now you could technically imagine more complex environments where maybe action becomes a vector, like a direction or something like this. But for now, we kept it simple, and this is still discrete.
Yeah, because if you would think about like an actual rat navigating a maze, instead of having these like clusters around these grid points,
yeah,
you would rather see continuous trajectories throughout the maze, right? And then would you still be able to get these clusters of locations in to transform these continuous trajectories into a discrete decision problem?
Yeah, that's a good question. It will definitely make it more challenging, I think, as the cluster may start to overlap. Now, like Gaussian mixture model are supposed to be resilient to that to some extent. But yeah, if it's fully uniform, it may be a problem. Something that may happen is that Gaussian is learned through, like along a corridor instead of for each cells. But yeah, I'm not exactly sure how the model will react. Initially, so here I've been explaining this model in the context of navigation. Initially, it was designed more as a way to try to get deep active inference to work. The idea would have been that you have images at the very bottom, a variational autoencoders extracting continuous features, and then you would try to learn a Gaussian mixture on top of that, turning it into a discrete latent space. And then you would have the expected free energy defined on those discrete latent spaces. So yeah, you are right that now that it's applied to like navigation, it may not fit perfectly. But it's because its origins come from trying to understand the latent space of variational models. So yeah, that's a good point.
Cool. Thank you for that. Lance has a question as well.
Yeah, hey Theophile, thanks for the presentation, super cool work. So I was wondering if you replace the GMM with an MDP, and instead of having the continuous observation space, you had a discrete observation space in a fully observed setting. I was wondering, I mean, obviously the task would be easier, but I was wondering exactly what would be easier. Like, do you think if everything was discrete and everything was fully observed, whether you would be able to learn the right model for all the mazes that you showed at the end, for instance?
Oh, I see. So is your question to like turn the observation into discrete observations to simplify the task and then see whether, yeah?
Yeah, and then basically you just had to learn an MDP and the right number of states in the MDP.
That's true. So this will definitely simplify the problem. So I haven't tried it, so it's difficult to predict how the model will behave. One of the tricky bits, though, about learning those red squares over there. So I suspect that this will be learned properly because it used to explore everything, so it will still explore everything, but it won't unlearn because there won't be Gaussian distributions. So I think this one will be solved properly. The performance on this one will also increase, probably matching DQN. This one still remains quite tricky, I think. The reason is because you are trying to discover the structure of the environment, but you don't have a model for the part you don't know yet. So you don't even know that there is something to discover over there. So you need to design the exploration strategy in such a way that if you already know the transition between the cells very well, then it becomes boring. And then you need to find a way to say, this is still exciting because I don't know exactly what's happening when I go left, basically. So in order to solve this maze, this is really like how you need to modify the exploration strategy in order to explore further. You need a notion of boringness.
Right. And during your presentation, you mentioned taking actions with respect to expected free energy or information gain. I presume that's what you think would solve the problem. Could you perhaps comment on how that would go?
So that's the question. I'm not even sure this would solve the problem, because information gain would only be about learning about the state we already know about. If you don't even know there is a state, you can't even compute information gain for them. So if you think about maybe there are 8 states already learned, but then you can't even compute information gain for those because it's not even represented in the model yet. Maybe another thing that could help, and in this case it's kind of information gain, but this time with respect to the parameters, it's the novelty term, which is also kind of information gain, but with respect to the parameters. The problem with these terms, so I tried a bit to implement it, but it's very slow. Like, in order to compute this, I think you have to compute like a Keil divergence between Dirichlet distributions, and this is computationally expensive. So it was adding quite a lot of burden to run it. So I kept it simple, and I stick with report. But that would be, I think, the most likely terms to solve the exploration problem. Yeah, indeed.
Right. And do you think it might be helpful to have a novelty term about the structure? If taking a particular action might reveal some information about the structure that you haven't seen before?
Yeah, I mean, that would be great if you could have another latent variable that represents the structure somehow, and then you would be able to have information gain with respect to this. The question is, how do you represent a structure mathematically using variables? That's a good question.
And I also have a question, if you don't mind, about the forgetting aspect of your model.
Yeah.
I was thinking about a different way of doing forgetting, and and I wanted to know how, to what extent it relates to what you've implemented. So one way I think one could do forgetting is that you get your data, then you find the right model to explain the data in the sense of minimizing free energy or maximizing model evidence. And in particular, you'd find the right structure. So you'd find the right number of clusters, for example, for your data cloud. And then once you have your trained model, you would discard the data points in a way that that the reduced data set contributes to minimizing the free energy further. And I think when you do that, so let's say you have 6 clusters of data, and basically what you want to prevent is to remove one of the clusters or remove informative data about the spread in each cluster. But I think if you were to do it that way, so let's say you have your trained model with 6 clusters, removing one of the data clusters would contribute to maximizing free energy.
I see.
So yeah, it's just like a general thought I had, and I was wondering whether you also thought about this kind of method and how it relates to what you've implemented.
So I've never thought about thinking about removing data points to maximize a variational free energy. To be honest, it could be useful for data points which are not fitting any component, for example. I think that's a kind of data points the model will discard first. So then you probably need to be careful not to just ignore new components because they don't fit the current model. But yeah, no, I haven't thought about that. So I haven't thought, for example, of the impact of removing data points and how it impacts variational free energy. That would be something which is interesting to explore indeed.
I think, as you point out, there's an important part would be the scheduling, and it would have to happen slower than the structure learning, because you basically want to find the right structure with all the data and then kind of like remove the data that you don't need. But yeah, it would be interesting to think about.
Yeah.
Thanks.
Yeah. Did you mention a paper which does this kind of methods?
I haven't seen it, but yeah,
okay. Yeah,
I mean, I'm sure it's there somewhere.
Yeah, to be honest, I haven't had time to look into like Bayesian methods in, related to forgetting or something like this. But yeah, there are probably people doing that.
Thanks, super interesting work.
Thanks for the questions.
Cool. Thanks, Lance. I think we can have like one more question. Owen?
Yes. Hi. Thank you. Very interesting work. My question actually is about your answer to the previous question. You said some of the state you don't know, so you cannot calculate the like the surprise. I didn't fully understand that part. So how does your agent interact with the environment? For example, when the mouse is in that location, how does the environment tell the mouse that you can go left and right, but not up and down?
Also, it can technically, like the agent can always take any action, but if there is a wall, that is kind of bumping into the wall, and therefore the agent is not moving. So if I want to be a bit more precise about the interaction between the agent and the environment, it goes as follows. So the agent starts in a state. The environment knows the current position of the agent. So it has it's sampled from a Gaussian centered at this position, and it returns a 2D position of the agent to the agent. That's the observation. Now, if the agent decides to go down in the initial position, the environment knows there is a wall, so it doesn't change the position of the agent and just sample another data point. So even if it has not moved, it will get a different observation and it will keep going.
I see. So in that case, agent is just doing a try and error. Its action is going to feedback the observation, and then from the observation, it will know slowly. It will know the environment. Then in that case, so if you go to the last one of your the zigzag snake type of a maze, in that case, isn't that between the green and red, the agent will know that it has never tried to go left on the boundary of the green yet, right?
Yeah, that's true.
And in that case, that will be a surprise that you can explore. That will be a signal for a surprise, right?
Yeah, so I think that's what is going to become like the novelty terms that we discussed a bit earlier with Lancelot. So the idea is that the parameters in the matrix which correspond to going left in this state is probably going to be very small, and so there will be potentially high novelty by taking left in this state. But there is still something that may be quite difficult for the agent to figure out, is that when it's here, it needs to plan all the way to here before it can benefit from this novelty term.
Right.
So in sense,
maybe I guess that means there needs to be a hierarchical kind of state in your agent's model, right? One is checking what it's doing right now, and the other one is kind of like remembering what it has explored and not explored. Yeah. That way you have a memory dedicated to the exploring strategy.
Yeah, that's true. Yeah, I think there's a lot of things to do, like with trying out different exploration strategy, potentially in like hierarchical models. But it's quite a lot more challenging. Like I wanted to just have a small version of the model for now.
Understand. Thank you. Thank you. It's very interesting work.
Thanks.
If there are no more questions, yeah, thank you everyone for your questions and comments. So maybe we can move to you, Carl.
Thank you. In fact, if there are lots of experts here who have been dealing with very related problems, I think it would be a shame not to invite them to talk. I was wondering if we could choose at least 3 or 4 people here, but I'm going to pick on Chris if he's still near the microphone. Could you, Chris, could you pretend to be the external examiner at a PhD and make some laudatory comments about consistency with existing approaches and what is, to your eyes, something you haven't seen before, which may be deserving of foregrounding and or exploring further?
You're
invisible.
Oh, sorry.
You are genuinely. You've got your invisible cloak on.
It's there. My camera's wrong. Let me do this. Oh, wait, I'll just turn this on. There we go.
Ah, that's one solution.
Well, that's it. You set me up with. I was multitasking. It was very interesting. It's very interesting stuff. And yeah, I mean, so this idea of we want to be able to operationalize the use of expected free energy and the ability to do this kind of counterfactual rollouts and epistemic stuff, but we know how to do that very well in discrete states, but not so much in continuous states. And Carl set out this path some time ago where we have to kind of integrate kind of a low-level control in terms of continuous active inference and this kind of higher level discrete kind of cognitive level where we can do all the planning is. And then it speaks very much to that kind of direction, which I really like. And I guess it's, one of the questions you've asking here, and we've been asking to some extent, is how do you do that combination? How you discover the right kind of discrete states to represent your continuous world, right? So you need to somehow segment your continuous observation space into a set of categorical states and then reason on that set of categorical states, right? And I think you've done some nice kind of groundwork to see, one particular way of doing that here. So I guess it's how do you do that segmentation is being a question on many people's minds, right? And this way, I guess it works to a degree. I think you kind of almost built in the segmentation into the discrete states by keeping the action space in quite a discrete manner, right? And then the observation space sits on top of that, so that it doesn't completely address this. How do we go from continuous spaces and the discrete and then discretize into some kind of discrete world which we can plan through? But I think this is definitely the right technology. I think Gaussian mixture models is by far the most promising avenue to do this, and indeed it allows you kind of to segment into clusters and then to use this kind of epistemics in the discrete state. So I really like this. I shared Tim's worry about if you don't discretize that action space and you're then going to have this mouse moving in a continuous space, how is this technology going to transfer to that domain? But yeah, I commend this direction. I think it's an exciting direction. Is that what you wanted to hear from me, Carl, or and Theophile, if you have any questions on that?
Yeah, no, I think that was very interesting. Yeah, just one thing about these actions. One also problem of having discrete actions is that you cannot really generalize across space. So ideally, you would like to have more of a vector representation of the impact of the action. So, going right is just moving the position to the right by one, this kind of thing. which cannot really be done with a discrete action space. So I think that's also one of the things that could be brought into the model to make it, better at generalizing. And then exploration may become even simpler if you just understand, if I'm here, I'm going left, it's just -1 on the x coordinate, for example. I think this kind of model will make exploration probably a lot easier.
So, one alternative that we've explored is to probably cluster in trajectory space with something like the kind of linear switching dynamical systems, right? And this gives you a much more natural way of then kind of clustering in terms of the dynamics rather than just in terms of the spatial attributes, right? And then having the transition represent the entirety of the spatial transitions. But yeah. But then this is really good. And are you intending to kind of put active inference in this? I worry that you said that many of the problems that you have here are not solved by the addition of expected free energy and that type of technology. So I guess my question is, what the next steps here then? Is it to try and augment this to make it work better, or to revisit the architecture?
So I think making it more stable first will be the next stage. So trying to get bigger and bigger problem, maybe with hierarchy, would be a natural next step. This is, I think, more complicated, but also quite interesting. But I think it has to come after a more stable model has been brought to the table. Because as you explore further, you are naturally going to encounter more states. And therefore, you need a stable model to keep learning new states. So I think that's
this allocation of Gaussian discrete states to better cover the space in a better way, right?
Yeah, exactly. Like, how do you avoid unlearning the components, basically?
The stuff on latent Dirichlet processes and all this type of stuff is a direction that you're considering.
Yeah, that's true. Like, I think Marek mentioned that could be an option indeed. I just didn't have time to try it out.
Yeah, that's apparently, I mean, we haven't tested them very much, but allow you to grow these things in an optimal way without having constraints on the numbers of clusters up front. But I think that might be, if that's the thing that you want to address, that might be the direction you should take. But yeah, I think this is overall for active inference, this kind of combination of continuous and discrete is definitely the way forward. And how do we do that carving up into discrete states in an optimal manner is something of great interest.
Yeah, one of the challenge I had about active inference in this context was a continuous aspect, and how do you even compute expected free energy when you have continuous state? It can be quite challenging. So I try to focus on only one problem first.
And I think Carl's committed to this idea that we don't do that, right? That we do as soon as possible within natural systems coarse grain into these spaces, and then reason in the coarse grain way. And I can see, you can think about that the way we reason. We take our world is deeply continuous, but when we do reason, like going to the airport, buying a ticket, it's deeply discrete, right? So I think there's an argument that that's an elegant solution, rather than trying to do expected free energy purely in the continuous, which requires you to solve nasty Fokker-Planck equations, I guess. But well, no, I think this is the right direction. Yeah.
Interesting.
Cool. Thanks very much. It was really interesting. Is that okay, Carl? Have I done myself?
Yeah, that was perfect. Yeah, you covered the fundaments and also the novel bits implicitly, and the particular challenge. So you can go back to your multitasking now. Thank you very much.
Well, great talk, Theophile. I really enjoyed that.
Did Theophile get his PhD, by the way?
Ah, right. Good point.
Does the external think it was worth a PhD?
He'll have to fill in the forms and write his report. Give him a few days. Tim, could you just make a quick comment about the relationship between Gaussian? If you're there.
Yeah, Carl, you're breaking up a bit.
Oh, I'm sorry. Can you still hear me?
That's better.
I was asking if you can still hear me. If Tim could just make a comment about the relationship between this approach and his adventures in Gaussian splatting.
Hey, yeah, I'm here. So yeah, yeah, just some context here. So one thing we are doing in the ML group here is using Gaussian mixtures in the Gaussian splatting sense, where basically when you imagine you have an RGB desensor, so you get color and depth information, you kind of get a point cloud of data around you. And then we use similarly Gaussian mixture models to kind of cluster these into Gaussians that represents where are obstacles and which color are they in space. And then you can kind of use these as landmarks for your agents to orient itself and navigate itself. So in this regime, it's like it's similar vein idea, like you get lots of continuous observations and you use a Gaussian mixture model to kind of discretize the space a bit, but while still keeping like the continuous world around you where actions can still be continuous, and you kind of use Bayesian filtering to work out where you are based on the things you see. Maybe while I'm on camera and talking anyway, so in your conversation with Lance, you had some exchange on like exploration and how can you do information gain for states that you don't know that they are there. I actually had some related work on this with the students from Ghent University, where we looked at exactly this, but then in a discrete grid world. So we didn't bother doing the move from continuous to discrete space, but we just tackled this exploration problem in grid worlds. And the trick we found was basically is that you kind of need to build a prior in your model about the things that you don't know yet. And what it boils down to in a navigation setting is that if you see a wall in front of you, then your prior tells you that there's likely no state beyond that one. But if you see open space or a door or something alike in front of you or somewhere in front of you, then you might have a prior built in that you might transition through the door to a novel state. And so basically what you do is when, like in your terms, if you encounter a new Gaussian component, you could kind of, instead of just recording the position, also record like some perceptual features of the surrounding of that Gaussian and learn like, if I see door-like features, then likely there will be something beyond the thing at the position after. And then you just kind of initialize a component or a state, or in your case, a Gaussian component beyond that point where you initialize the probability that you can transition to that according to your prior. So if you see a wall, then this prior is almost zero, and you might not even bother creating the state. But if you're not sure what is there, you do already create kind of this component, and this will then encourage your agents to kind of try to find out whether it can reach that spot, and then you get kind of the information gain of active inference doing its thing, having your agent explore the whole maze as efficiently as possible. So maybe that might be useful for this work as well, if you want to go in that direction.
I see. So just to make sure I understand, it's basically in that you extend the observations. So that's, for example, if the agent is here, it's also observing maybe in front of him. So you get a second observation which tells you whether there's a wall or an open space here. Then you can use that
exactly.
to set prior preferences in the state space.
Yeah, so you need to equip your model with kind of an extra layer that's given the kind of space you see. You have some expectation on what will be near that space, and then you can already kind of ingest some extra states with like a uniform prior. You don't know what is there, but you think something is there, and put like the transition, the prior transitions in your tensor accordingly, such that your agent thinks like there is something there and I can reach it via this this state I just saw. I don't know whether the chat is working or not, but else I'll just email you the paper that I'm talking about for reference.
Yeah, sounds good. Thanks a lot.
Could I ask a question of Tim? Sorry, just for clarification. So I've come across Gaussian splatting, but that's just a mixture of Gaussians, right? Or is it something different? Is it just computer scientists talking about something in statistics, or is it different or what?
Well, so in the ML literature, so Gaussian splatting is indeed just a mixture of Gaussian. The only thing that is kind of peculiar is that they, like, given your mixture model, you use this and some camera viewpoint in that space, you basically use a differentiable renderer to render pixels as if you were looking from the camera to that mixture of Gaussians, and they and you kind of do alpha blending and so on, but in a differentiable way, so that if you then actually get your camera frame, you could use backpropagation through this renderer to optimize your mixture model. So that's kind of how
cool. Yeah.
How they typically do it in like the Gaussian splatting world, but nothing withholds you to do any other like also Bayesian optimization techniques on the Gaussian mixture model, which is kind of the thing that we are exploring here. Like, can you do it using variational Bayes? And the answer is yes.
Great, thank you.
Thank you, Tim. I've been left alone now. Right. Magnus, did you want to say anything about Bayes optimal forgetting?
I don't think I have anything to add that hasn't already been covered. But thank you, Theophile. This was a very interesting presentation.
Thanks.
Right. Okay. Well, let me try and bring things to closure and summarize. So just a couple of points that came up in conversation there. This overall endorsement of getting from a continuous state space representation into a discrete state space where one can do the right kind of planning as inference, I think was one of Chris's basic messages. He gave the examples of going to the airport. Another sort of more physiological example are place fields. You know, the very fact that we have discrete representations of being in this place or that place in our hippocampus, I think is a nice testament to the potential utility of being able to quantize or discretize the scene and your navigation through that scene. So I just wanted to make that point. And you can generalize that argument not just to place fields, but to receptive fields in general, speaking to the way that we sort of carve nature at its joints, or the functional form of the implicit or requisite generative models. The conversation with Tim, you know, one of the key points that sort of came out again in discussion was the distinction between exploring an environment, possibly with expected utility or rewards somewhere in that environment, with a very myopic view of the world, namely you can just see where you are, or you can just sense if you can move in one direction or another direction, as opposed to having the ability to look around you. And that takes you into the world of Gaussian splatting, it takes you into the world of scene construction, it takes you into the world of having potentially a discrete generative model of some space where you just don't know what is occupying each point in that, for example, gridded space or discrete space. So At the moment, you have to move, the rat has to move to find out what is there. If you equip the agent with the ability to see, not necessarily everything, but certainly be able to see in front of it, with or without occlusion by the walls of the maze, then that takes you to a different level, which I think may well be which would afford the kind of solutions that Tim was talking about, and would certainly be the kind of approach that you would use if you were trying to simulate artifacts that were exploring their environment with some aim in mind. So, one canonical example in industry here is equipping a drone with active inference, but also with the imperative to do some search and rescue to find a climber with a broken leg, for example. So I'm just reiterating some points have been made that may be useful in terms of thinking about what problems are soluble within the particular setup that you've been focusing on, relative to the problems that might be more easily solved with a slightly more expressive generative model, and equipping it with vision, basically, or LiDAR or something of that kind that provided a more information about what would happen if I did that. But having said that, I just want to turn to the brief you've set yourself. And it strikes me you're trying to solve a number of problems, which is good, but also makes it quite difficult. You're trying to solve the structure learning problem. You're trying to solve resolve the exploit dilemma, and do it computationally using variational procedures in a hybrid model with continuous and discrete state spaces. And I'm just wondering, just standing back, whether your device of first learning the mixtures with the perceptual model, and then having got precise beliefs about the mixtures, then learning the transitions, whether one might generalize that, in the sense that, in my experience, you probably have to do your structure learning before you can do your exploration and novelty seeking, before you can then go and get your reward or your bit of cheese. So, as Lance said, the scheduling of the various optimization problems at different levels in terms of the structure of the generative model, the number of mixtures, the parameterization of the generative model, namely the parameters within that structure, and then the inference that rests upon the precise beliefs about the parameters, sometimes yields to appropriate scheduling, just solving one problem at a time. But my sense is that you have taken the interesting challenge, which may well be faced by real agents, of trying to solve them all together. So can I just ask you, as time goes on, and you the number of clusters that you have inferred changes, does that mean that the size of your discrete latent state space Z also changes with time?
Yes, exactly. So this also brings some challenges that I've not been speaking about, but for example, the size of the matrices changes. So you need to extend the size of the matrices dynamically, and you need to keep track of all parameters. So imagine you have a small matrix, you discover a bunch more components, you get a bigger matrix, and now when you do the tracking of the Gaussian, you know which previous components correspond to the next components. Okay, so this one corresponds to this one, and you now are in the business of copy pasting from the small matrix to the big matrix, the parameters, so that you don't forget what you have already learned about the environments.
And I'm guessing that difficult job of not losing information, but also being sufficiently flexible to accommodate a different structure as new information becomes available, was a motivation for this partitioning into what to forget and what not to forget. Would that be one way of looking at this?
Yes. So initially, like the initial motivation for the split was really performance. The idea, because if you don't forget ever, then initially you have 100 data points, then you have 200, then you have 300, 400, and to compute the parameter of the posterior, you generally have to do more and more computations. So it was a way to cut the amount of computation that you have to do.
Right. I'm going to suggest that that you may have ended up doing this careful dissection of data into that which can be installed in the empirical priors versus that which goes on to inform the variational posterior, because of this difficult problem of doing the structure learning on the fly and also accumulating evidence in the form of Dirichlet parameters, certainly at the discrete level, simply because this notion of you need more and more compute as you have seen more data is resolved, if not dissolved, by the Markovian nature of this problem setting. So just because you're dealing with a Markov decision process, or you're implicitly dealing with, but the dynamics here are explicitly and only a Markov decision process, that means that you can look at each time point as a Bayesian belief update in which the yesterday's posterior becomes today's prior. And as such, you shouldn't increase the compute time as you're accumulating evidence. So I was a little bit confused about what to forget versus what not to forget, because of course that just is Bayesian belief updating. It's just basically assimilating data by using the posterior up until the current time as the prior for the next data point. And if you just assimilate those data under the condition that the data are conditionally independent, you will get the Bayes optimal result. That's the whole point of Markovian processes, or a generative model of Markovian processes. If I am right in that, that means that you were, I think, trying to solve a more subtle problem with this sort of forgetting and not forgetting. And I'm just wondering if, well, what's your response to that? The only time you need to use Bayes optimal forgetting is when the environment is changing. So there are situations there, say, for example, the cheese is in a different position, or some doors are open and shut. So there's a degree of volatility in the environment. When there is a degree of volatility in the environment, when you're accumulating Dirichlet parameters about the shape of that environment, then it is wise to lose or to forget if you think that there is uncertainty or there are dynamics on the very position of the walls or the cheese. And that's a very interesting problem. And that's normally how I would read the importance of forgetting. Whereas you don't seem to be actually forgetting, you just seem to be installing certain parts of the history of the data into empirical priors and other parts into the variational posterior.
I see. Yeah, so that's a lot of good points. Another reason for forgetting is the structural learning part of things. The fact that we are still discovering components, so even the size of the matrices are being expanded. So the idea of not doing just Bayesian updates like you mentioned, using Bayesian filtering or something like this. Those methods are fine if you already know the size of the matrices. But if you are still discovering the components, I found it beneficial to keep track of all of the data points, like to have some kind of short, not short-term memory, but more like a buffer of past experiences. So it would be more, I'm not sure how the brain will implement that, but more maybe in the hippocampus or something like this, where, for example, rats can replay past experiences. So this kind of memory, and this allow you to group things together. Because if you forget, like using what you mentioned, you will only have the last data point, basically. So finding clusters to learn this mixture of Gaussian becomes even more challenging, because now you have forgotten all of the past data, and you don't even know. I mean, you would have to have some way to remember where the clusters were. So I think that was one of the motivations for keeping some data in the first place, and not just using some kind of just Bayesian filtering or like Bayesian updates.
Yes, yeah, I mean, and that is exactly what I was implying, that you were using this this device of forgetting and not forgetting or partitioning exactly to solve the problem of doing online structure learning and parametric or parameter learning at the same time.
Yeah, exactly.
I say that because if if you haven't already, when you write this work up, I would foreground that as the particular problem that is being addressed by the machinery that you're bringing to the table, because that, to my mind, was one of the novel contributions here. I have not seen this partitioning into forget and not forget before. So I was wondering, why on earth do you need it? And I think the reason that you need it needs to be made very clear. And you need it because you are tackling the difficult problem of doing structure learning and parametric learning online at the same time. So just thinking about strategies that one wouldn't usually, or one could bring to the table to address that problem. One way of thinking about this is in terms of splitting and merging, and literally in terms of the likelihood mappings from the Zs to the mu's, the centroids of your clusters. When you create a new cluster, one can think about that as basically creating another column of likelihood mapping from, in this instance, Z to, I would imagine, mu, and at the same time, by implication, equipping B with an extra row and column. So you've got the opportunity now to accommodate another cluster or distribute the Dirichlet counts between now two states, so that you've now got you're now, if you like, splitting your previously one latent state pertaining to one locational cluster into two, so that they're now learnable as distinct things, but you're not forgetting the accumulated knowledge that pertains to this pair. And then the equivalent merge operation is just basically adding columns of the likelihood matrices to each other, so that what were previously two states now become one state, but you're not throwing away the Dirichlet counts. And that can be just implemented with a simple reduction matrix, which just has sort of noughts and ones, and has more than one on the columns, so that you are reducing the size of the likelihood matrix, and you apply exactly the same matrix to reduce the size of the transition matrices. So that might be one way of looking at the problem, that you're now dealing with evidence accumulation, both at the level of consequences of action and inferring states such as where I am or which cluster I'm in, but also in terms of the parameters of the generative model at the level of accumulating the Dirichlet counts, looking at this as putting on top of this a split and merge capability that is informed by the history of what you have seen, or by not forgetting certain things. And while I'm saying this, the terminology to forget may mislead some people. I don't think you mean forget. You just mean store in a particular way that you can't redistribute over new clusters. Whereas there are other Dirichlet counts or bits of evidence, associations or conjunctions that are still open for allocation as you increase or decrease the number of clusters. Would that be a fair summary of one description of the procedure you've been using?
Yeah, I think that was a very fair summary, to be honest. I think I really like the notion of online structured learning, and I think that really helps clarifying what we are trying to do, and do that at the same time as doing the parameter learning, for example. So that's very useful.
Excellent.
For the forgetting, I think you also have a point. I mean, I'm not sure we use this term, or maybe we do. Yeah, but okay, I see what you mean by forgetting when it comes to like volatility versus the kind of integration of evidence we are doing.
Yes.
Yeah,
perhaps immortalizing might be another way of putting it. Can I just see your equation where you show the accumulation Dirichlet counts for the two, for the E and the Qs for the Dirichlet counts?
Yes, sure. So I think
yeah, brilliant. Yeah. So in effect, if the empirical one is really just sort of placing those effectively in fixed clusters, you're basically immortalizing that evidence, saying that that's no longer up for, these things are always there, and they're going to be part of the structure irrespective of the other clusters, which are more mortal in the sense that they can go away and die, or they can be split into two clusters. It's just that when I look at those equations, that for me is evidence accumulation, which is not forgetting. And also the other nice thing about this equation, if you substitute the top line into the second line, then your n is over the entire data set, which is what it should be if you were just doing standard basic belief updating and accumulating all the evidence under the assumption that nothing in this maze is moving around. And that might be a nice way to something to explain to the reader, that you're basically just splitting you're splitting the evidence accumulation in the spirit of basic belief updating into two sorts, where one sort means that it is immortal and immutable and has a commitment to a particular latent state, whereas other Dirichlet parameters or evidence of associations or contingencies are potentially redistributable over subsequently new clusters or discrete or latent states.
Yeah, exactly. And that's exactly how those equations were derived. I started with the posterior equation, and then I tried to pull apart the part which was depending on the forget, the data point to forget, and the one which are to keep. And there are like other equations for update, especially for the perception model, which are more complicated than that, but it's exactly the same process. You start with the posterior update equation, you do some mathematics to rearrange it, and then you realize that, oh, in fact, you can split this into two parts. The first one is going to be the update for the empirical prior, and the second one is going to be for the posterior. So that's a very good point.
Excellent. Okay, and finally coming to this vexed issue of exploration in these tortuous environments where you need to be at a point where it's you can explore. It reminds me of people going to the base camp of Everest as a journey in itself before they can start climbing the mountain. My limited experience of this, my experience is much more with learning the likelihood mapping as opposed to the transitions, but the maths should be exactly the same. But my limited experience suggests that I think you should just revisit and pursue the full expected free energy that includes the novelty term as a way to solve that sort of snake-like problem and the left on the in the middle row on the left-hand side. And that's because it sometimes is the case, even the absence of vision, that you form very, very precise beliefs about the fact that moving up, for example, from the start location leaves you where you are. And therefore they become boring. So that the only interesting option is to move in a direction which you can move in. And after, it almost inevitably, it is moving out of that dead end that is the thing that must have been done least often if you stayed there long enough. And then you can apply the same argument to moving along the corridor. So in principle, you should get a gradient of novelty, which, as you properly intimated, is very simply encoded in the number of Dirichlet counts effectively in the transition matrix. So you can now imagine a gradient of novelty, which might, if you're lucky, pull the agent to where the green meets the pink, simply because there's no other way to go. So I mean, and the novelty computation is very simple. It's exactly the same that you'd apply to the likelihood mapping, but it's just applied to the columns of the B, the transition matrix. And if I remember correctly, you can actually just write it down as in the form of a Hadamard product, I think, between the posterior over ZT plus 1 and Z outer product, and then element by element with a single matrix. That's a relatively simple, I think, involving beta functions or log beta functions that you can pre-compute if you knew the structure. So what I'm saying here is that if you've done good structure learning, but you and you know there are states, but you know the profile of the states, but or the number of the states, but you still have some residual uncertainty about what's occupied. Say you don't know where the cheese is, then you might be lucky with the right scheduling and be able to show that the inverse boredom or the novelty, i.e. the information gain on the parameters, itself has gradients through action space, even if the action space doesn't actually have a proper metric. But that argument does rest upon knowing the structure. So you'd have to solve the structure learning problem first, and then invoke the expected information gain on the parameters to properly explore the space in an even-handed way, so that you become equally familiar with all parts of the space. And I think that would become interesting if the cheese could move around. So if you had a problem now where the cheese is not something that you're learning as part of the structure, or indeed as part of, well, yeah, it could be the parameters, but that would be an instance where you would have to, in the usual way, forget where the cheese is, because the cheese can move on every trial. But as soon as the cheese has been placed, is hidden somewhere else, then that evokes a certain novelty that can be resolved by looking here and then looking there and then looking here and then looking there. So it might be that if you choose the right problem, which is slightly more difficult than just finding where the cheese is, identifying the location with the cheese, but finding where the cheese is on any given trial, then you might be able to tease apart the structure parameter learning of the maze, and then use what the agent has learned about the maze to then solve the exploitation when looking for cheese that can be in different locations. Does that make sense?
Yeah, it does. I'm also very interested in this notion of, like you mentioned, the Hadamard product, like for the computation of the novelty term. So I think at some point I was looking inside the MATLAB code, and I saw that. I was like, I'm not sure how they came up with this equation, Do you know like whether there is a paper somewhere which explain how you turn a Dirichlet distribution into this kind of matrix multiplications?
Yeah, I think there was a table in a paper by Thomas Parr and Peter Ziedman on Bayesian model reduction that gave you the expected information gains for a number of the exponential family distributions, including the Dirichlet. And it's exactly the same equation that you would use for the likelihood mapping and the probability transition tensors, because it basically applies on a per column basis, if I remember correctly. So if you can't find that, email me and I'll check, and then I'll send you a link to that paper.
Sounds good. Thanks a lot. That's very useful.
Good. Well, no, thank you. Yes. Yeah. So. Yeah, well, just to conclude, of course, the limitations of this to speak to the ambitions or the goals. The failure on the large square on the bottom, yeah, it is due to this. How do you solve the joint problem of structure learning and parameter learning online? It's interesting you found a failure, and you've already discussed a number of potential ways of finessing that failure under the current technology. And the other interesting issue is then having done your structure learning, coming to the snake problem and getting exploration into the game, and we have discussed that. So it's nice you've got the two key goals, and also ways of measuring if you have met those goals implicit in the limitations, which will speak to future work as it should do. So thank you very much.
Thanks a lot.
Thank you so much, Carl. Yeah, let's give a round of applause to Theophile. Thank you so much.
Thanks to everyone. Brilliant.
Thank you, Carl, as well.
Thanks a lot.
Yeah. Thank you, everyone.
Thank you.
Bye.
Okay.
See you, everyone, in the next
Bye-bye.
TMB session. Bye.
Bye-bye.